think we should get going. I appreciate you all being here. It's been a crazy day. It's been a crazy day here. I'm John Griffith. I'm a curriculum developer with the Cooperative Institute for Research and Environmental Science. It's an organization at the University of Colorado Boulder. Coming to you live from snowy central Vermont. I work remotely. Um, and these are some of my favorite parts of my job. I spend a lot of time working alone developing resources, but my favorite part of my job is to share them with you all and to get to work with folks to bring contemporary science into classrooms. So thanks for being here today. This is a brand new data puzzle. We'll talk about what a data puzzle is in just a moment. But a brand new lesson. It's called Not All Warming is Equal. Brand new lesson, but not a brand new data set. In fact, some of you who have worked with me previously may recognize the data set from a previous unit that I developed. But I thought that there were some really compelling stories from the data that may be buried in these larger units. So I wanted to pull them out to create a more concise product where teachers and students could engage with these data sets. So like I said, we'll spend the first 30-40 minutes talking about data puzzles, what they are. We'll engage with the Not All Warming is Equal data puzzle, talk about some strategies for implementation, and then we'll have Dr. Schneider come on at the end to talk about his work as a climate scientist. I think, yep, we're recording this. So if this becomes a resource that you want to look back on, I'll make sure I'll share that resource with folks via email after this. We'll also share the slide deck with you all, as well as some other resources. I know that because there's just a lot going on in this amount of time here, I'm going to show you, this is a landing page. So this will be something I'll email out as well. And I'll add it to the chat right now. So kind of just a record for you to keep of things that we'll discuss today. There's a link to the data puzzle website. The slide deck I'll be referring to. If folks are interested in receiving a webinar certificate, a 1-hour PD webinar certificate, there is a link to that Google form. And then a link to all of the different resources that are a part of this Not All Warming is Equal data puzzle. So links to the teacher guide, slide deck, student worksheet, answer key, everything is here. Oh no, thanks for the heads up. We'll do it live so everybody can see. So you might need to refresh it. Thanks, Mike Javat. Appreciate it. So there we go. We got some other folks in there now. Anonymous Bat, welcome. So links to the Not All Warming is Equal resources, and then some links to some upcoming data puzzle webinars. My colleague Elise that's here today, she's working on a Winds of Change data puzzle. She'll talk about at the end of February, but we thought we would try to get as many of these in at the beginning of the semester, just in case folks might be interested in trying to implement one or more before the end of the school year. So again, this will be kind of a living document. I'll add the recording here when we've uploaded it to YouTube and share that out via email likely tomorrow. What else am I missing? Success, good. Everybody's in there. Introductions, Google Forms. Let's get this party started. So for those of you that don't know who I am, I'm John Griffith. Again, I work for this Series Education Outreach team. I'm this talking head for a hugely collaborative group that has supported me and encouraged me to develop this data puzzle instructional framework and these individual resources. My supervisor, Dr. Anna Gold, has been instrumental in the development of these. Elise and I work closely in the development of these data puzzles and a data library. Hint, that's coming. So trying we will continue to build these curated data puzzle lessons, but try to include more data sets on our website so folks can take those data sets and tell stories in their classrooms without that polished product that we produce. Amy Schmidt here, she's a graphic designer who's just awesome, makes these data puzzle lessons what they are. And then collaborators at the University of Colorado Boulder, really fortunate to be able to work with Dr. Melissa Bratton, a co-author of Ambitious Science Teaching. These are instructional practices that we've embedded into data puzzle lessons. So it's been huge to have her help us develop this framework and these lessons. And then scientists like Dr. Jen Kay. Jen is the featured scientist in this Not All Warming is Equal data puzzle, but we're fortunate to get to work with lots of scientists from the University of Colorado and beyond to bring their research into classrooms. Also want to shout out to teachers across the country who have piloted these lessons and given us feedback. So again, I'm the talking head for this really great team, and look forward to continuing to work with these folks and others for years to come. Our journey here with data puzzles actually started in 2019. Many of you here were there with me from the beginning, with the onset of the Mosaic Arctic Research Expedition. So I was hired in 2019 to connect the public to this historic Arctic research expedition, and we developed weekly newsletters, activities, larger units, and developed quite a following. And when the field portion of the expedition ended, we had teachers asking for more, asking for data sets from this expedition that can continue to connect their students to. And so we curated some data sets with the help of Mosaic scientists, and reached out to our friends at Michigan State who create data nuggets. I'm sure that's a resource many of you are familiar with. And so we worked with the folks at Data Nuggets to create this product. And while we loved the product, we wanted a little bit more flexibility. We wanted to integrate some of these different instructional practices as described by Ambitious Science Teaching. So we wanted to kind of do our own thing, and that's where data puzzles came about. So again, trying to use data to tell compelling stories, but using these research-backed instructional practices. And so you'll see in our library, we have maybe more data puzzles right now focused on what's happening in the Arctic, just because that's where a lot of the funding initially came from. But we'll continue to build that library out this year and in years to come. For those that might not be familiar with Ambitious Science Teaching, it's a pedagogical framework with practices and tools that support meaningful and equitable science education. And so it provides strategies to plan for engaging with important science ideas as described by the next generation science standards, for eliciting student ideas, language, and experiences that can be used as key resources for making sense of science, strategies and tools for working with those student ideas, those student resources, to support ongoing change. And then how do we press students to construct evidence-based explanations? So strategies for that as well. And so we've taken each of these 4 practices, we've kind of rearranged the order of a couple with permission from Ambitious Science Teaching authors, and kind of integrated them into a 2 to 3 day lesson. You'll notice in our instructional framework, we do not ask you to plan for engagement. We do the planning for you. And so our data puzzles instructional framework, obviously very similar to the practices as defined in Ambitious Science Teaching, but we start in data puzzles by eliciting student ideas. So trying to reveal resources students bring to the classroom about an opening scenario. And the opening scenario has similarities to the science investigation that's presented in the data puzzle. So before dropping students in the Arctic and saying, let's explore albedo of the Arctic, like maybe we can find an opening scenario, an example related to that students can connect with that has that has components of reflectivity before we bring them to the Arctic and explore the albedo of the region. So connecting to students' personal lives before introducing this science investigation through a puzzle plot, a 2-page interactive text that students will read together to learn a little bit more about a science investigation and a featured scientist. And students will pull out some of the big science ideas to develop initial models and predictions. Students will test those predictions by analyzing a data set curated and or collected by the featured scientist, and then they'll put all the pieces of the puzzle together to construct a final evidence explanation. In most cases, that's a final explanatory model. So almost very similar to the ambitious science teaching circle, we've removed the planning piece and instead done the planning for you. And so this is the data puzzles framework. And from here on out, we're talking about the data puzzle framework in the context of the not all warming is equal data puzzle. And so just a reminder, in that landing page, there are links to the lesson homepage, the teacher guide, the slide deck, student worksheet. Actually, I've learned that it's best practice to show that off, just so you know what's available to you. So from the data puzzles page, clicking around too much right now. From the data puzzles page, if you select collection, takes you to our library. Here's the not all warming is equal data puzzle we're talking about today. We've got data puzzles related to mega drought, ecological tipping points, shifting patterns of post-fire succession, offshore wind farms, among other contemporary topics. If you click on view resource, it takes you to the resource page. All resource pages look the same. There's a little bit of information about the lesson, context for use. Basically, it's a data puzzle that uses ambitious science teaching practices, events, what students will do, and then these teaching materials. So these pages look the same for each data puzzle. I'll point out that this teacher guide has a draft watermark because it has not been classroom tested yet. It's in the process of being classroom tested, but so just want to make sure that we set a high bar for ourselves and make sure that what we're putting out in the public is being rigorously reviewed by scientists, tested in classrooms, so that folks can trust that these are ready to go. Page 2 of all the teacher guides, connections to the next generation science standards, driving questions, what student will do statements, and then materials that always include the slide deck, teacher guide, and answer key. So we include the answer key in the teacher guide. I know students are really skilled now at searching these things online, so I try to hide it here. I haven't heard from teachers that it's been a problem, but students are really savvy at this. So hopefully by hiding the answer key in the teacher guide, they at least have to work a little bit harder, but those are the resources that are available to you. So what we'll do now is go through each of the 4 parts of the data puzzle together in the context of this not all warming is equal data puzzle, so you can get a feel for what to expect, what the purpose of each part is, and then what you can expect in the context of the not all warming is equal. So diving into the first part of each data puzzle lesson, this is that eliciting students' idea quadrant. And again, the goal here is to bring out student ideas about an opening scenario. This is typically a video, an image, or a demonstration that's going to have similarities to the science investigation presented in the data puzzle. So just want to make it clear, this is more for me. These are not included in the student worksheet. This is something that we've had teachers do as warm-ups in a science notebook. as think, pair, share activities, or teachers have distributed whiteboards to have students work in small groups to think about their individual experiences and create lists together that they'll share out with the class. So the goal here for teachers is to bring out student experiences, ideas, and language that can be used as resources later on in the lesson to help students make sense of new complex science phenomena. So again, things like if we stick to the albedo activity, if you're in an area that's has snow and you're like, well, why is it so, like, if you go outside on a snowy day, like, why does it feel so bright? What's going on with that? Or in the winter, like, it seems like it's lighter when there's snow on the ground later into the evening. What's going on with that? So trying to connect to student experiences and getting students to share those experiences. Those resources are really valuable for teachers later on while they connect those experiences, while helping students connect those experiences to a new phenomena. In the context of the not all warming is equal data puzzle, we ask students to think about a time they've been outside on a hot summer day. Maybe they're playing basketball in their backyard, walking the dog, outside by the pool. But imagine that the thermometer reads 100 degrees Fahrenheit. Is it 100 degrees everywhere you are outside? Are there some places where it might feel hotter, some places where it might be cooler? Like, from students' experience, is it the same temperature everywhere outside, or can you find places where there are these different temperatures? So getting students to think about a hot day, where they might hide out or where they might go if they want to get really scorching hot, like these different areas with different temperatures. And then connecting that back to kind of what's going on in terms of the global climate system, where, like, outside on a hot day, it's not the same temperature everywhere you are. And that's kind of the same thing globally. Temperatures are on the rise globally. And just like your neighborhood, some areas are warming faster than others. And that's how we would segue from a personal experience to introducing Dr. Jen Kay, who's the featured scientist in this resource. She studies changing global temperatures, and she understands that rising temperatures caused by the burning of fossil fuels by humans is driving this change. But she sees from her work that some parts of the world might be warming at different rates than others, and she's eager to learn a little bit more about that. So from student experience, transitioning from that student experience into the introduction of a featured scientist who studies something similar to that student experience. That's how we transition into the distribution of a puzzle plot text. So these are the 2 to 3 page synopses of what that featured scientist does for their work. And so here's where I would distribute student worksheets. And the goal of part 2 here is to support students in identifying important science ideas introduced in this interactive reading called a puzzle plot. And so I'll show you a picture of what that looks like here in a second. Those are linked on that landing page. But the goal here is to connect science ideas from the reading back to that opening scenario. So again, connecting student resources to a new science phenomena. We have students summarize key ideas by creating an annotated sketch or by looking at a sketch and describing what they see. So some way to bring out some key ideas. And then students are asked to identify an investigative question, which is called out in the text, and make a prediction about the question the scientist is seeking to answer. I would say most classes that we've worked with have elected to read the puzzle plot text aloud together, because there are videos and graphics and things to talk about and engage with together. That seems to be the most popular facilitation approach. We have had teachers have students read them individually or in small groups. Others have integrated their own close reading strategies to support students. So we would encourage you to do that as well. In the slide deck that goes with the lesson, what we have students do is learn more about Dr. K's research by reading this puzzle plot text, and you would decide whether students read it individually or as a whole class. We ask students to circle the investigative questions scientists are seeking to answer and then underline similarities that they might identify between the reading and the opening scenario. And so in the slide deck for the lesson, we have slides with specific prompts that ask students to consider how the reading and opening scenario are similar. So again, trying to use student resources, connect student experiences to this new science phenomena. Hopefully make it support student sense making in that way. The puzzle plot for this data puzzle looks like this. 2-page puzzle plot starts by talking about the greenhouse effect, defining a greenhouse gas, showing an image here, a diagram on the right that shows the sun's energy reaching the earth, infrared or heat energy escaping from earth. And you can see this would be an example of a greenhouse gas, a gas that absorbs and re-emits this infrared radiation, this heat energy released by Earth. So from this graphic, we ask students to describe what a greenhouse gas is, those characteristics, and then we get into this historical context, describing kind of the start of the Industrial Revolution, the increase in the combustion of fossil fuels, and then the increase of these greenhouse gases in Earth's atmosphere. So getting students to think about like, all right, if we see the behavior of a greenhouse gas and we had more of them, what might we expect? And students watch a video that talks about greenhouse gases kind of acting like the steroids of the climate system, and then interpret this graph here that shows temperature in the blue line, global temperature anomalies, and how they've changed with respect to increasing carbon dioxide concentrations since around the start of the Industrial Revolution. So again, trying to make the case, right? Like, here's what greenhouse gases do. We've been putting more of them in the atmosphere, so we can expect, as we have observed, that temperatures have increased. Trying to really make the connection, more CO2, increase in temperature, drive that home for students. So after engaging with that text collaboratively as a whole class, you can see with videos and sub-questions buried within that text, you can see opportunities for that to be collaborative. We asked students to describe why global temperatures have increased since the start of the Industrial Revolution, asked students to document this investigative question, which in the text reads, do the places on Earth where temperatures are increasing the most also have the greatest increases in atmospheric carbon dioxide? So we see this relationship globally. More CO2, temperatures have increased, but our temperatures aren't increasing in the same way globally. Some places they're increasing more rapidly than others. And does that have to do with CO2? Do the places where temperatures are increasing most also have the highest changes in carbon dioxide? We have students make a prediction about that question. And here's what that looks like on the teacher guide. So again, wanting you to get familiar with all the resources that are available here to you. The teacher guide, the answers that you might see show up in red. So this is kind of an important summary of ideas describing why global temperatures have increased since the start of the Industrial Revolution. We provide these graphics. Pre-revolution, fewer greenhouse gases in the atmosphere. After the start of the Industrial Revolution, more greenhouse gases in the atmosphere. And so we ask students to describe what they see, what they notice, observe about these differences in the space below here. Students identify the investigative question and then make a prediction about that evidence, about that investigative question. And then they'll test that prediction in the next part, supporting ongoing changes in thinking. I'm just gonna keep rolling here in the interest of time. I'll note that the summer offerings that I have are a little bit longer, and we can dig into these different parts together in breakout rooms and in a more collaborative way. So wanted to just put a plug in that. We'll put those summer workshops out, but we're gonna kind of keep rolling here with the resource and take some questions at the end as they come. So students have made this prediction about the investigative question, and now it's time to analyze a data set to test their predictions. Some facilitation strategies here based on the work from folks at Ambitious Science Teaching. Super important to talk about the graphs in small groups as a whole class before asking students to analyze those data sets on their own. Heard from a number of teachers that they use this whiz-wim strategy as not only as a way to introduce data sets, but as a way to support the analysis. Whiz-wim means what I see, what it means. So students basically write what they notice on a graph or a map, and then write what it means in that space. So annotating the graph as a way to make sense of it. With the not all warming is equal data puzzle, we first introduce how Dr. Jen Kay gets her data sets. So she runs climate models, these simulations that use mathematical equations based on known processes to predict past, present, and future climate conditions. So this is the work Jen does, and this is the way that the data sets in this resource were derived. And so a brief introduction about those climate models, and then looking at some data collected by these climate models that show how temperatures and carbon dioxide concentrations have changed from the early 1900s to the early 2000s. So here's the first one of the first graph again, and this is a slide directly from the slide deck for this resource. This is also included in the student worksheet. This is a change in surface atmospheric carbon dioxide. So this figure is showing the change in atmospheric carbon dioxide in parts per million from 1900 to 1914 to 2000 to 2014. So basically, we have the average atmospheric CO2 concentration from 2000 to 2014 and subtracted out the average concentration of atmospheric CO2 from 1900 to 1914. And this is showing the difference in average CO2 for those two time periods. What you'll notice here is that all across the globe, atmospheric carbon dioxide concentrations have increased. The lighter yellow here, an increase of a concentration of 107 parts per million. The darker, deeper reds representing an increase in CO2 concentrations up to 123 parts per million. And so before having students analyze this data set, worth having a conversation as a class about what the different colors mean, maybe identifying some different locations, specifically the United States. What color or colors do we see in the United States? What does that mean in terms of atmospheric carbon dioxide? So just by looking at this, we can see some interesting patterns. In Northern Hemisphere had a greater increase in atmospheric carbon dioxide than the Southern Hemisphere. We see a couple different colors in the US. Some deep red colors over China. And so asking students to kind of discuss this, what they see, what they think it might mean. We do the same thing for the change in temperature data set. So just similar to the CO2 data set, this figure shows changes in surface temperature from the 1900 to 1914 average to the 2000 to 2014 average. So again, average temperature from 2000 to 2014, subtract the average temperature from this 1900 and 1914 period. And this, what we see here is the difference in average temperature of those two time periods. Again, introducing this data set, asking students what the different colors represent. What do they notice? What do they wonder? We've got spaces on Earth that have actually cooled over time. The vast majority have seen dramatic increases. Nowhere do we see more dramatic warming than in these northern latitudes, the Arctic, up to 4 or 5 degrees Celsius temperature change from that 2000 to 2014 time period with respect to 100 years earlier, the 1900 to 1914 time period. So introducing these data sets, having students talk about what the different colors represent, maybe identify specific points on Earth, the United States, for example, having students describe those conditions there before turning students loose and asking them to identify and explain patterns in the data and evaluate their prediction for the investigative question by taking a look at the student worksheet. The student worksheet, I wish I had pulled this up, but I can do it real quick. The student worksheet for this looks like this. After the puzzle plot, after they've identified some of those important science ideas. So the data sets show up just as they would in the slide deck in that order, having students interpret the change in atmospheric CO2 data sets, getting them think about the different colors, some different patterns, interpret those patterns. Do the same thing for the change in temperature, that change in temperature plot here. Different colors, different patterns, and then we ask students to revisit the prediction here. I'm seeing a question from Mike Jensen, who's in Canada here, and I appreciate your question. And something I should have noted earlier, these resources are all available in Google products. And so we would encourage you to make copies of these resources and to modify them to meet the needs of your students or your locations or whatever it is that you need to do. So, Mike, the possibilities are endless. In fact, what we would encourage you to do is once you open a teacher guide, open a student worksheet, encourage you to make a copy of that resource, pull it into your own Google Drive account or pull it onto your desktop and feel free to modify these resources as needed. I tried to make them as plug and play as possible. Being a former middle school science teacher myself, like it's really nice if you can find something that you can just use with students that requires little modification. So they're written in this way, but also you just elected to use Google products because we know that it's pretty easy. A lot of teachers use Google products. It's really easy to make copies and modify them yourselves. Thanks for the question, Mike. The last part of each data puzzle, this constructing evidence-based explanations, like at this point, probably looking at day 3, we're 120 minutes or so into class. We've elicited student ideas. We've collaboratively engaged with that puzzle plot text, answered a few questions. We've looked at a data set together. And so now we've got all of these different pieces of evidence that we've gathered, and we need to put it all together to construct a final evidence-based model. So in the slide deck for the actual lesson, we've got some slides that show an example of an explanatory model. So students that might be less familiar with an explanatory model and data puzzles is kind of an annotated sketch. So we provide an example of what we're kind of looking for and some signs and symbols that students could use: arrows, zoom in windows, keys, timelines to show changes over time. So check that out in the slide deck. But what we have here for a final model, we've created a similar map to what students have seen in the data sets. So it's that same map of the globe that was behind the change in CO2 and change in temperature data sets. And then we have a key thermometers with different levels of temperature, cars, smokestacks. And we asked students to consider, like, how could you use thermometers to show changes in temperature? And so they could refer back to their data sets, right, and say, okay, temperatures change greatest in the Arctic. So I might use the thermometer that's full up in the Arctic. Temperatures changed maybe less so in some of these other regions. So I'd use the low thermometer there. You wouldn't just tell students this, but these prompts are designed to get students to think about how they could represent those science ideas in an annotated sketch. Smokestacks in cars, how could you use that to show changes in CO2, right? You could put more cars, more smokestacks, maybe in certain areas than others. And get students thinking about what evidence they have from the text or the graphs, encouraging them to use numbers in this final explanatory model for the question, the places on Earth where temperatures are increasing the most, are those also the same places experience the greatest increases in atmospheric carbon dioxide? And looking at those graphs, right, we don't see that relationship. Arctic is warming much more rapidly than other parts of the Earth, yet that's not where we saw the greatest changes in atmospheric CO2. Here's an example from the answer key. It didn't copy over well, but you can see some of these thermometers that are full up in the northern latitudes. I've referenced some data from the graph, increase of temperature by 4 to 6 degrees Celsius relative to that 1900 to 1914 average time period. We've got some cars and smokestacks that are impossible to see here. Sorry about that. With different change in atmospheric carbon dioxide concentration numbers here. So ways to use symbols and numbers to represent science ideas that come out of the data set students analyzed. All data puzzles also end with some digging deeper questions. So getting students to think about more deeply into the why or how, or a social justice issue related to the science phenomena being investigated in the data puzzle. In this case, I've included 2 digging deeper questions in this lesson, but like Mike alluded to earlier, you can make a copy of this lesson and modify it as you see fit. The first digging deeper question that I've included, and students might ask this, and we've got resources related to it, but rising global temperatures have caused sea ice to melt. How might the decline in sea ice lead to even more warming in the Arctic? So trying to hint at, and students might ask, why is the Arctic warming more rapidly? Like, there's sea ice up there. There are very few people. Why is that an area on the globe that's warming faster than other places? So getting students to think about that and perhaps hint at a mechanism driving that amplification up there. So seeing what students think about that. And then a second digging deeper question, thinking about climate inequities and some of the social justice issues around climate change. The fact that there are 4 million people living in the Arctic that call this place home. They emit a very small amount of carbon dioxide in the atmosphere relative to folks living at lower latitudes. So it's safe to say the warming in that region is related to the behavior at folks that don't live there. So asking students to think about, do the countries that emit the most CO2, United States, China, Europe, those places on the change in CO2 map, these places all showed up in that a redder color? Should those places have to pay for the damages that the Arctic and other developing countries are experiencing because of climate change? So a question that policymakers are grappling right now in a lot of spaces, and an interesting way to pose it to your students. Tons of resources out there, videos, articles that you could connect and bring in here as well. So that's the not all warming is equal data puzzle. So again, we've gone through that, eliciting students' ideas about an opening scenario, thinking about a hot day. Can you find places outside on a hot day where temperatures might be different? and you can, and that's the same thing with the global climate system. Some places are warming more rapidly than others. We see from the data set that the places that are emitting the most CO2, seeing the greatest changes in CO2, are not necessarily the temperatures that are the places that are experiencing the greatest rise in temperatures. So from the data set, we've constructed an annotated sketch, an explanatory model to represent the data that we've just analyzed, and then some digging deeper questions to think about, well, why is that area warming more rapidly? And social justice issues around, well, those people are experiencing these really rapid changes in temperature, but didn't cause that change. Like, is that fair? Who should have to pay for it? So hopefully you can see the thread through this and how you could introduce a really important topic to your students with this lesson. I want to put a plug in for next week's webinar here, to reflect or not to reflect. It's a really good lesson to follow this one. It challenges students to think about that amplified warming in the Arctic by looking at sea ice and albedo data sets from the region. There's a wildfire and future of forest data puzzle that's brand new. I'll be talking about that in a couple weeks on February 7th. A new lesson I hope to publish online next week that looks at changing snow conditions in the Rockies and consider how the implications for the downstream water users of the Colorado River. And then Elise will be on the end of February to talk about the hazards of strong winds in the Rocky Mountains and how those winds may be changing or not in different climate conditions. So you have the slide deck in that landing page, and also these events are listed on that landing page with registration links should you choose to join in the future. Know that these are all being recorded, and so if you do register, you'll receive a recording even if you can't attend the actual date. So tons here. And before I take questions from you about the lesson, I want to make sure I give Dr. David Schneider, who's here, some time to share a little bit about his work as a climate scientist, answer questions you might have about the data set that we just looked at in the data puzzle, or other climate model related questions. So and Dr. Schneider is an experienced climate scientist. He has experienced and does research integrating observations and climate model experiments of past and present to predict future climate events. So really a perfect person to join today. And Dr. Schneider, I'm wondering if I could stop sharing my screen and turn it over to you.
Yeah, hi. Can everyone hear me now?
We got you.
Okay. Hi, John, and hi, everyone. Yeah, it's exciting to join you to talk about a data puzzle. And I think this example is like a really good example of the types of questions we ask as scientists, the types of questions we're asking every single day. So I think it's giving you a good example of what we do. And you can just call me Dave. You don't have to call me Dr. Schneider. So maybe I don't want to take up too much time. I'll just give you a real quick rundown of my work and background. So currently I work at Ceres, which is the same institute that John works at, and I'm in the group that's led by Dr. K. And before I came over to Ceres, I was at the National Center for Atmospheric Research, or NCAR. And one of the things that NCAR does is build climate models. So some of those slides you saw actually came from the climate models that we built at NCAR. Probably the most exciting part of my career was actually going to the polar regions, both the Arctic and the Antarctic. But then to make sense and understand what's going on there, and to make predictions about the future, we use climate models. So one of the projects I have going on right now is about the question of why the Arctic is warming 4 times faster than the rest of the world. One of our hypotheses has to do with the role of clouds. So, as you know, cloudy days can be different than sunny days, and there's all kinds of different types of clouds. So clouds can be kind of gray, or they can be bright and white. They can be made of ice, or they can be made of water. So clouds can have all types of different properties. So if you think about that example that's in the slide deck about the thermometer says it's 100 degrees, but it's not necessarily 100 degrees everywhere. So if you wanted to go out and make an observation of like, is it warmer where clouds are, when clouds are there or not warmer, that would take a lot of observation and be really messy, because not only you have to control for, is it cloudy or not cloudy, you have to think about, well, which way is the wind blowing when it's cloudy or not cloudy. And so that's really hard to like pinpoint the role of clouds just by going outside and making observations. And so that's one of the things we can use climate models for and do a really controlled experiment. So we have an experiment A and experiment B can have the same winds, but all we do is just change the cloud property. And then we can see if that makes it warmer or colder. So that's the kind of question we can answer using a model. So that's one of the ways we're looking at why the Arctic is warming much faster. It could be that both the amount of clouds and the cloud properties are changing. And then, so we'll look at what happens in the model experiments and then compare them with real world data and see if our hypothesis is correct. So I'll stop there. Looks like there's only a little bit of time left. So let's have questions.
Hey, Dave, thanks for being here and thanks for that little bit of background about yourself. There's a question from Gina in the chat. I'm not sure can you see the chat?
Yeah, let's see. I didn't read the question.
I can read it aloud or give you some time to read it.
Okay. Is it this one about Wisconsin?
Yeah.
Yeah, so you're trying to interpret trends in Wisconsin and historical trends 1950 to 18 versus future projections 2041 to 2060. So it might depend on what kind of trend you're looking at. If you're looking at temperature or snowpack or precipitation, it would depend what type of model you would use. So the type of model I'm talking about is good for really large scales, like the continent scale or the global scale. But if you're looking at a kind of small region, the state of Wisconsin, or even a region within Wisconsin, we want to use a more detailed, what's called a regional model to look at that. So we get a little more complicated. But certainly there are data sets from both these global models and from the regional models that are available.
Gina, do you want to hop on and elaborate or ask some other questions? Feel free to do that.
Yeah, I guess we've done a lot of work or used the wiki resources in our lessons that we have. So they'll have a map of like what's the nights below freezing in Wisconsin, from the historical data set, and then what are the projections for the nights below freezing. And so they have the great images similar to what you have in your slideshow already for like the worldwide temperature changes and then the worldwide carbon dioxide. And so what I'm wondering is, could we work with K-12 educators, and our goal is to increase energy awareness, climate ed, and we have funding from forestry department in the DNR as well. And so I'm going to attend your wildfire workshop later
great.
because I think that would be great as well.
Yeah.
But wondering, like, could we use the model that you have and insert some of our own graphs specific to Wisconsin to share with our Wisconsin educators to help them, bring a local perspective on climate into their classrooms?
Yeah, with the models we have, we can get it kind of regional. You have to do what's called downscaling to kind of get it really local.
No, but I
We
guess
get
what
sort
I'm
of a
saying is, like,
general, yeah, we can get a general picture.
And
Wiki
Gina,
has Wiki
I
has
think,
done the downscaling. I'm just looking at, like, I guess when I say model, I'm looking at your lesson model. So like,
yeah,
could we look at using your lesson model with the wiki data, because they've done the downscaling for Wisconsin and have
Okay.
the maps. So I would take your lesson example, plug in the wiki maps and use some of those same questions and find a scientist that works at Wiki. I know my boss is on the committee for land use planning in Wisconsin with Wiki, so she can probably connect me with somebody. But would you be okay if we used your, like, lesson outline format?
yes, yes. Thanks for, sorry, Gina, that took me so long I should have interpreted what you were asking sooner,
What
but
I did, I should have used
yeah,
a word other than model.
yes,
Okay.
yes. So absolutely, please do that. The only thing that we would ask is that you don't use like our series header footer on it. But we are absolutely trying to inspire others to use this instructional framework to create their own lessons. We would just ask that because we didn't make it, you made it, you would put your name on it. But other than that, yes, feel free. And if you want to take the maps, the data sets, like from our lesson and use it into something else that you create, please, by all means. This is nothing proprietary here, wanting to just like connect students to high quality climate education resources. So yeah, that'd be great. I'd love to take a look at what you produced too, Gina.
Yeah, wonderful. I have a couple of projects on my plate for this spring, but it's definitely something I would work on this summer, and I will share whatever we come up with.
Great.
So thank you.
Thanks, Gina. And hey, Renee, while you're here, when I'm giving this kind of like broad answer to your question because it's like not my life's work, but 3 or 4 years of resources related to the Mosaic expedition we've developed, and they're still coming. So that NOVA documentary is excellent, and we have like tons of things, VR tours. We've got planetarium shows. Mike Jensen runs a museum up in Canada and has worked with some planetarium shows. We've got data puzzles, larger units, so lots of things. So if something comes to your mind that you might want, we've probably got it. So you've got my email in that landing page. So
Yeah.
please reach out to me. I'd love to work with you to help you find what you're looking for.
Yeah, we're in New York. We're just transitioning to well, they're calling it New York State Science Learning Standards, but basically it's the NGSS.
Yep.
So we're all kind of struggling on, like, how are we going to get there? And so this is, this kind of thing is I think is really awesome.
Great.
So thank you for this. Yeah.
Yeah.
I'll sign up for some more of your workshops.
Yeah. Well, thanks for being here. I appreciate it. Get a lot of
Yeah.
folks from New York and Wisconsin area from that Spirit listserv, which I'm sure is where
Yeah, the Esprit.
Yeah.
Yeah, I've worked with Mike Jabot before too. I'm an officer for the New York Earth Science Teachers Association. So I can certainly have our webmaster post some of the data puzzles website, at least up on our website, as long as that's okay with you.
Yeah, that'd be great. And
Yeah.
if there are, again, like Elise and I, we talk about this as former classroom teachers, like we miss the camaraderie of working with people, and would love to, if there's a school district that wants to learn more about a specific resource, or happy to tailor these talks to meet the needs of teachers in specific districts. or in bigger spaces. So if you feel like New York, if there are pockets in New York that would like to hear more about this, I'd love to chat with them.
Yeah, well, we have the infamous Regents exams at the end of the year.
Yeah.
Which everybody seems to know about. So, you know, like they're kind of restructuring the format of of the Regents, more geared more toward the NGSS stuff. And so we're all going, oh no, how are we going to do this? So I think these are wonderful.
Great. Thanks, Renee.
Mike says he doesn't run
Yeah,
these.
sorry, Mike.
Thank you.
Yeah.
I like to think I run it sometimes, but I don't really run it.
Well, that's it for me here. I think one thing I wanted to add is the link to a Google form here in the chat. It's in the landing page, but if folks want a certificate for being here today, please fill out that Google form. If you don't want a certificate, feel free to ignore that Google form. That Google form is in the chat. Just want to get your name and email so I can send that out to you. It'll likely come in your inbox tomorrow. Awesome. Thanks, Gina, for sharing that resource. I'll be sure to add some resources to that as well. If folks don't have any more questions, feel free to hop off. We hope to see you again in the weeks to follow. We'll be here every Wednesday for a little while. Thanks, Mike. Thanks, Amy. Thanks, Dave. Appreciate you being here. See you, Gina. Looking forward